This is an example implementation of tic-tac-toe using Unity and Rulebook. This example is meant to showcase hot reloading, automatic testing, and imperative-based coroutine programming. Let us now play a round of tic-tac-toe. As you can see, when we click on cells, they get the color of the current player, alternating between blue and red. When a player owns 3 inline cells, the game terminates, and the engine prevents us from clicking on the remaining cells. Okay, then let us take a look at how it is implemented. This is the rulebook file that contains all of the information about the logic of the game. Beside imports, there are 2 top-level objects. One of them is the class board. Board contains 9 slots, and those 9 slots must be integer, bounded between 0 and 3. 0 means that it belongs to no player, 1 it means that it belongs to the first player, and 2 it means that it belongs to the second player. Similarly, we have a boolean that tells us who is the current player. Then we can see various helper functions that will tell us, for example, if the board is full, if there are 3 in a line either vertically or horizontally, and if there are 3 in a line anywhere on the board. Finally, we can see as well that there is a getter to see the current player and a method to go to the next turn. This class looks exactly like any other class that implements the board of tic-tac-toe in any language. The following function is more interesting. If you have never seen a rulebook program before, do not worry about the unknown keywords that you have never seen. Instead, focus on the rules of tic-tac-toe. The rules state that 2 players alternate each other marking empty squares on a board until the board is full or one of the players scored 3 in a row. The code here resembles the same idea. Play is the starting function of the game, which allocates a board of type uppercase board. Then, while the board is not full, there exists an action called mark. This action accepts x and y as arguments, and both x and y must be between 0 and 3, 3 excluded. On top of that, there is a precondition. The location at x and y of the board must be equal to 0, that is, the slot must be empty. If that is the case, then we can execute board.set, which will set the location at x and y as belonging to the current player. Finally, if there are 3 in a line belonging to the current player, the game ends. Otherwise, we move to the next turn and the loop resumes. Okay, we can now look at hot reloading. Let's start the game again. Then let's go into the code and let us add an extra precondition. We want to say that the user is only allowed to write in any cell that is not on the second column. The graphical engine immediately reacts and let us know that we cannot click on the last column. Okay, but maybe what we actually meant was that we can only write on the last column. We flip the condition of the loop and the engine automatically updates. Now let us say something more complex. We want to say that if a player clicks on the last column, that player is allowed to take a second move. We specify this by saying if x is equal to 2, then we repeat the same action as before by copy-pasting it as is. We can go back to the engine and see that when we click on the last column, we are allowed to click on 2 different cells, but only when we click there. Okay, this was hot reloading. But there is more. Did you notice that we inserted a bug while we were editing the code? Let's look at the code again and consider what happened if the last square of the board is marked while it belongs to the last column. In that case, since x is equal to 2, then another mark action is allowed to be performed by that player. But the precondition of mark specifies that only empty cells are valid. Therefore, there is no valid cell that you can mark. While this may be acceptable in this particular scenario, usually the fact that you have not reached the end of the game is a symptom that there is something wrong in the rules. For this reason, let us look at automated testing. With Rulebook, you can use the built-in fuzzer to automatically look for this kind of bugs. We can see in this terminal that we are in the same location where there is the file that contains tic-tac-toe, and we can show it on screen with cat. Then we can simply invoke RLC with the -- fuzzer option. It will create the fuzzer, which we can then run and use it to look for bugs. The fuzzer immediately stops and tells us that it has saved on disk a crash report. We can re-execute the fuzzer, passing the crash report as an argument. If we do, we are immediately confronted with the nature of the bug. There is a list of 9 actions that have been executed on the game. Those 9 actions terminate with the action mark with x equal to 2, which is exactly the bug we were looking for. On top of that, the fuzzer tells us what is the problem. It has found a combination of actions that leads us to a situation where there are 0 valid actions. Using a debugger or other methods, you could investigate the bug, but we already know what it is. So let us fix it. We just add a condition to check that the board is not full. Then we can recompile the fuzzer and run it to see if the bug has disappeared. That is it, we have fixed our bug. Now we can run the fuzzer for a longer time and see that nothing crashes. As a recap, we have written the play function in an imperative style that did not require us to explicitate the update functions. Then, while Unity was running, we changed the rules of tic-tac-toe however we wished. Finally, we automatically test those rules and found that there was a bug and fixed it. These are only some of the capabilities that the rulebook enables. You can discover other techniques such as automatic remote execution and automatic generation of reinforcement learning tools in the documentation linked below.